Welcome to the pod Biomanufacturing and Fermentation Technology. In this episode, we translate microbial science, process engineering, and manufacturing realities into insights that scale.
So imagine you take a massive, locked safe, packed with gold bullion, right? And you drag it out to the middle of the ocean, and you just dump it overboard.
Yeah, and imagine doing that every single day.
Exactly. Every day, simply because you don't happen to have the combination. I mean, for decades, that is essentially what the industrial manufacturing world has been doing with its wastewater.
It really is.
When you look at a large facility, whether it's manufacturing petrochemicals or refining paper or even processing food, there is this rigid, almost psychological line drawn between the product and the waste.
Right, the product is the asset.
Yeah, you manufacture the thing of value, and whatever liquid is left over is just viewed as a toxic burden. It's an environmental liability that requires millions of dollars in operational budget just to neutralize and discharge.
And that has always been the baseline assumption, right?
Yeah.
I mean, industrial effluent has historically been treated as this necessary evil of production. The entire goal has just been mitigation.
Just make it less bad.
Exactly. You measure success purely by whether you can avoid a regulatory fine when you release that water back into a river or a municipal sewer.
But today, we are taking that fundamental assumption and completely flipping it on its head. So if you're listening to this deep dive and you operate an industrial plant, or if you study bioprocessing, the way we look at this liquid is changing. Completely.
It's a massive shift.
It is. Industrial wastewater is no longer just a liability. It's actually a highly valuable carbon reservoir. It is a nutrient stream. It's this untapped platform for bio-based resource recovery.
The paradigm shift here is profound. We are no longer talking about merely making water clean enough to legally throw away. We are talking about actively mining that water for commercial value. The liquid coming out of the back end of a facility is now, well, it's a secondary raw material.
But to make that leap, it requires a serious technological bridge. And that's our mission for this deep dive. We are going to unpack the emerging microbial and hybrid bioprocess strategies that are finally providing the combination to that locked safe.
Which is so crucial right now.
Yeah. We're going to explore how biological systems are being engineered at scale to convert complex industrial effluents into value-added outputs, shifting from just basic compliance to a fully integrated circular bioeconomy.
And I think the stakes for mastering this transition just cannot be overstated. If you're a biotech executive or, a plant manager or an engineer listening, this is rapidly transitioning from a nice-to-have sustainability initiative into a core commercial necessity.
The economics are forcing it.
Absolutely. The underlying economics of waste management are changing so aggressively that facilities continuing to treat their effluent as the sunk cost will soon find themselves, frankly, structurally unable to compete. You can't compete with someone who is upcycling their waste into secondary revenue streams.
Right. But to understand how we actually achieve that upcycling, we first need to take a hard look at why our historical methods are failing us today. Let's look at the actual task at hand. What is happening on a molecular level inside these industrial waste streams that makes them so incredibly difficult to manage?
It fundamentally comes down to the highly recalcitrant nature of industrial effluents. We need to differentiate this from standard municipal wastewater.
Which is mostly just biodegradable organic matter.
Exactly. But industrial streams are packed with complex xenobiotic compounds.
Let's break that term down for a second because it is central to the problem. Xenobiotic essentially means a chemical structure that's been synthesized by humans or altered by industrial processes that nature just hasn't yet evolved the biological machinery to easily digest. Is that right?
That is a perfect way to look at it.
Yeah.
These are molecules literally designed by nature or by human chemistry to be durable. I mean, we're looking at melanoidins, which are these dark, incredibly complex polymers. They're what give distillery and fermentation waste its unyielding brown color.
And they block sunlight and waterways, right?
Yes, which kills aquatic life. We're dealing with phenolics, polycyclic aromatic hydrocarbons, or PAHs, high concentrations of ammonium, synthetic oils, heavy metals. They actively resist decay. And conventional physicochemical systems, the legacy infrastructure we've relied on for 50 years, they struggle to break them down either economically or sustainably.
Because those legacy systems were built for a totally different era. They were built to brute force the problem using physics and heavy chemistry.
And that brute force approach has resulted in 4 major bottlenecks that are currently paralyzing industrial scaling. So first, there is a staggering operational energy demand.
How staggering are we talking?
Huge. To get naturally occurring bacteria to eat even a fraction of this waste, plants have to pump massive volumes of oxygen into giant aeration basins. Those industrial blowers run 204/7.
So they just consume an exorbitant amount of electricity, which hits the bottom line immediately. What's the second bottleneck?
Excess sludge generation. When you use chemical precipitation, meaning you add iron salts or alum to the water to force the contaminants to clump together and settle out, you aren't actually destroying the toxic compounds.
You're just changing their state.
Exactly. You are just moving them from a liquid phase into a solid phase. That creates literal mountains of toxic secondary sludge that must be dehydrated, transported, and stored in specialized landfills.
So you're literally trading a water pollution problem for a solid waste problem.
Precisely, which leads to the third bottleneck, incomplete degradation. Even when the legacy systems attempt to break down the chemistry, they rarely achieve full mineralization.
And mineralization means breaking a toxic organic molecule all the way down into harmless inorganic components like carbon dioxide and water, right?
Right. But instead, the legacy systems often just chop a highly complex toxic molecule in half. So you're left with slightly smaller, but sometimes equally toxic intermediate byproducts.
That's terrifying. And the fourth bottleneck, which I assume brings us back to our safe, is the complete lack of resource recovery.
Exactly. You spend millions on energy, you pay landfill fees for the sludge, and at the end of the day, you extract zero value from the carbon and nutrients that were in that water. It's a one-way street of capital loss.
You're spending massive amounts of capital to destroy potential resources. It sounds like trying to use a sledgehammer to do the work of a chemist. It takes a massive amount of kinetic energy, it leaves a huge unusable mess, and half the time, the original problem is still just sitting there in pieces.
That's a great analogy.
But if the industry has recognized these 4 major bottlenecks for decades, why are we only now seeing a shift? Why has it taken so long to move toward simultaneous detoxification and recovery?
Well, the reality is that until very recently, we lacked the biological tools to survive the environment. Historically, wastewater treatment relied on naturally occurring wild-type sludge communities.
Just whatever microbes happen to be around.
Yeah, that operator essentially threw whatever generic microbes aggregated in the vat at the problem, crossed their fingers, and hoped those microbes could survive the toxicity. We didn't have the genomic sequencing, the synthetic biology, or the precise algorithmic process control required to engineer and maintain highly specific microbial consortia.
The sledgehammer was basically the only tool available.
Right. But today, bioprocess engineers have developed the biological scalpel.
So let's look closely at that biological scalpel, because this is where the action really starts to accelerate. We're talking about engineering microbes to do the heavy lifting that toxic chemicals and brute force aeration used to do.
And the specificity of this engineering is what's driving the commercial shift. We are no longer relying on that generic, highly vulnerable sludge. We're deploying specialized engineered microbial consortia.
Give us an example of that.
Sure. A brilliant case study from the recent research highlights a specific bacterial strain called Paracoccus pantotrophus. This specialized strain has demonstrated an incredibly high efficiency for decolorizing those stubborn melanoidins and degrading aromatic pollutants.
What stands out about the Paracoccus pantotrophus strain in the literature is not just that it eats the pollutants, but how it operates chemically, because it accomplishes this under low-energy static conditions, right?
Which directly attacks our first major bottleneck, massive energy demand. Traditional microbes need dissolved oxygen forced into the water to fuel their metabolism. But this engineered strain is metabolically adapted to utilize different electron acceptors.
Oh, wow.
Yeah, it can break down complex aromatics without needing those massive industrial blowers running at full capacity, so the energy footprint just plummets. However, the true breakthrough in these modern consortia isn't just a low oxygen appetite, it's their metabolic adaptability.
Let's dig into that mechanism. What exactly does metabolic adaptability look like inside a microbe when it is swimming in a vat of industrial effluent?
Well, think about the physical reality of an industrial plant. The wastewater composition is never uniform, it's highly volatile. At 9:00 a.m., a chemical plant might flush a stream with a massive concentration of phenols.
Okay.
By 2:00 p.m., That same effluent stream might suddenly be spiked with heavy metals or, experience a severe drop in pH. When wild-type generic microbes experience that kind of shock, they undergo cellular stress and die en masse.
And then what happens?
Your biomass washes out, the treatment process crashes, and you start violating discharge permits immediately.
But the engineered consortia handle that differently.
Yes, because they're designed with genetic and metabolic plasticity. When that 9.00 AM phenol spike hits, the microbes dynamically upregulate a specific set of enzymes designed to metabolize phenols.
They adapt on the fly.
Exactly. And when the environment shifts at 2.0 p.m. to a high heavy metal load, the microbe essentially flips a genetic switch. It downregulates the phenol-eating pathway and activates a stress response pathway, perhaps secreting a binding agent to protect its cell membrane from the metals.
So it literally changes its diet and its physical defense mechanisms in real time in response to the chemical environment. That is wild.
It really is.
But, okay, engineering a highly adaptable microbe in a sterile, perfectly controlled laboratory is a phenomenal scientific achievement. But taking that microbe and dumping it into a million-gallon open-air tank at a pulp and paper mill is a completely different reality.
Very different.
Right. So how do engineers actually maintain control over that environment so the microbes can actually do their job?
Well, scaling this up to industrial volumes requires bioprocess engineers to perfectly balance a highly specific trifecta. 1, controlled redox balance. 2, oxygen transfer optimization. And 3, stable microbial community dynamics.
It sounds incredibly precise.
It has to be. You have to sculpt the exact physicochemical environment where your expensive engineered microbes can thrive and basically outcompete any useless or invasive bacteria that blow into the tank.
You mentioned redox balance. For the listener who might be, a few years removed from their last chemistry class, redox reduction and oxidation is basically the transfer of electrons between molecules. It's kind of like the chemical voltage of the water that dictates what kind of biological reactions can even physically happen, right?
That is highly accurate. Bacteria essentially use those electron transfers to breathe and eat. If the redox potential of the water shifts too far in one direction, the microbes you want will literally suffocate, even if there is food available.
Which sounds like an absolute nightmare to manage manually. I mean, if you have to maintain the perfect redox potential, the perfect oxygen transfer, and perfectly stable community dynamics in a vat of constantly fluctuating, highly toxic chemicals, it seems physically impossible for a human operator to keep up.
It is.
So how exactly do we manage that delicate balance without the system crashing every time the factory changes its production run?
We manage it by realizing that biology alone cannot solve this at an industrial scale. We have to move away from viewing microbiology as an isolated field and start integrating it directly with advanced hardware and algorithm control.
Ah, okay.
This introduces the concept of hybridization. We are supercharging the biological scalpel by marrying it with advanced electrochemical engineering.
The sources refer to this as electro-biological systems.
Yes. We are integrating electrochemical separation directly into the microbial conversion platforms.
Stop there for a second and paint a visual for us. What does an electrobiological system actually look like when you walk up to one of these massive bioreactors? Are there just giant metal rods dropped into the water to electrocute the waste?
No. You won't see sparks flying, but you will see highly advanced electrodes and anodes and cathodes integrated directly into the architecture of the bioreactor itself. We apply a very specific, carefully calibrated, low-voltage electrical current through the wastewater.
So you aren't shocking the microbes?
No, we are giving them a precise electrochemical assist.
And how does that assist them exactly?
By combining electrolysis with microbial catalysis, you actively drive the chemical reactions the microbes need to survive. For instance, the electrolysis of the water can split H2O molecules, providing microscopic nanobubbles of oxygen directly to the bacterial cell membranes.
Which I assume is way more efficient.
Phenomenally more efficient than using giant blowers that just churn the water. With blowers, 80% of the oxygen just bubbles up and escapes into the atmosphere anyway.
Wow, okay. That solves the energy-intensive oxygen transfer problem beautifully.
And it does much more. This specific hybrid approach is proving incredibly effective for simultaneous ammonia recovery and wastewater detoxification.
Ammonia is notoriously difficult to deal with in wastewater. Usually it either off-gases into the atmosphere as a severe pollutant, or you have to dump heavy chemicals into the water to strip it out. How does the electrical current change that?
Well, the electrical gradient actively influences the ions in the water. The positively charged ammonium ions migrate toward the cathode, and we can physically separate and capture them through specialized membranes, while the microbes in the main chamber continue to metabolize the organic carbon.
Wait, really? So you aren't just neutralizing the ammonia?
No, you are harvesting it.
Yeah.
You get detoxified water out of one pipe and recovered commercial-grade ammonia out of another. And ammonia is a highly valuable commodity chemical for fertilizers and manufacturing.
That directly addresses the resource recovery bottleneck. That's brilliant. But what about the physical vulnerability of the microbes themselves? Even with an electrical assist, floating freely in a tank of xenobiotic compounds seems incredibly risky.
It is risky. In traditional suspended sludge systems, the bacteria float around individually, which leave their cell walls completely exposed to toxic shock loads. But engineers have induced a brilliant structural evolution known as algal-bacterial granular sludge systems.
Granular sludge. This is where the algae and the bacteria naturally aggregate together into dense, highly organized spherical structures, right? It functions almost like a microscopic industrial co-op.
That is an excellent way to conceptualize it. Inside these tiny granules, you have a perfect symbiotic exchange. The algae utilize light to produce oxygen through photosynthesis. The bacteria right next door use that exact oxygen to metabolize and break down the toxic organic pollutants.
And then the bacteria release carbon dioxide.
Yes, and the algae then capture that carbon dioxide to fuel their own growth.
It's literally a closed-loop supply chain at a microscopic level. But how does that aggregate structure actually protect them from the toxicity of the industrial chemicals?
Because as they aggregate, they secrete what are called EPS, or extracellular polymeric substances.
Which is essentially a thick, gelatinous matrix they build around themselves.
Exactly. Think of EPS as the concrete, and rebar the microbes pour to build their own protective fortress. This enhanced EPS formation acts as a highly resilient bioshield against sudden spikes in toxicity or heavy metals.
That's fascinating.
It leads to dramatically stronger biomass stability. And because these granules are dense and heavy, they also settle out of the water rapidly via gravity. That completely eliminates the need for the massive, energy-intensive secondary clarifiers that legacy plants use to slowly filter out suspended sludge.
The mechanics of that are incredible. But taking a step back, managing an electro-biological bioreactor filled with thousands of specialized granular biofortresses, all while the influent chemistry is wildly fluctuating. We are clearly way beyond the era of a human operator walking out with a clipboard and checking a pH dial every 4 hours.
We are well past human empirical control. And that is why the ultimate operational game changer in this field is the integration of machine learning. The industry is currently deploying multi-objective optimization frameworks driven entirely by artificial intelligence.
Let's push back on that a bit because AI is a very popular buzzword right now, but physics are physics. If a machine learning algorithm is trying to optimize a plant for maximum sac reduction chemical oxygen demand, meaning we want to destroy every single trace of pollutant, that inherently requires more energy, more retention time, and more biological activity. But if the algorithm is also tasked with optimizing for energy efficiency, it wants to throttle the power down. Those are fundamentally competing physical goals. How does a digital framework mathematically reconcile that for a commercial operator?
You've hit on the exact limitation of traditional linear control systems, and frankly, why machine learning is the only viable path forward.
Yeah.
In the past, human operators managed by reactive guesswork. If the sensors showed high CA, the operator would manually turn the aeration blowers up to 100% just to be safe, which wasted staggering amounts of electricity.
Just burning cash.
Exactly. The AI frameworks don't guess. They use predictive mathematical modeling. They continuously ingest thousands of data points per second from real-time sensors influent toxicity, flow rates, real-time redox potential, temperature, and electrical conductivity.
And what does it do with that torrent of data?
It maps out what engineers call a Pareto front.
Let's visualize a Pareto front for the listener.
Imagine a curve on a graph representing the absolute edge of physical possibility. A Pareto front is an algorithm that finds the mathematical sweet spot where you achieve the maximum possible pollutant degradation for the absolute minimum energy input at that specific millisecond in time.
Okay, I see.
Any movement away from that curve means you are either wasting energy or leaving pollutants in the water. The AI continuously surfs that exact curve dynamically. It might drop the electrochemical voltage by a fraction of a volt while simultaneously extending the hydraulic retention time by 2 minutes.
Wow.
Yeah, it balances COD reduction, energy efficiency, and process economics simultaneously. It shifts biomanufacturing from reactive human guesswork to proactive, predictive digital control.
All right, so we have thoroughly covered the task, the incredibly stubborn xenobiotic waste. We've explored the action, the biological scalpel of engineered microbes, the electro-biological hardware, and the AI optimization. Let's move to the result. For the biotech executives, the plant managers, and the chemical engineers listening right now, what is the hard commercial reality of deploying this?
The hard metrics generated by these hybrid bioprocess strategies are undeniable. First, facilities achieve significantly reduced hydraulic retention times. Because the granular sludge and electrochemical systems process the chemistry so rapidly, the wastewater spends much less time sitting in tanks.
Which means?
That means a facility can process exponentially higher volumes of effluent using a much smaller physical real estate footprint.
And as we discussed earlier, the aeration costs plummet because of the biological efficiencies.
Dramatically. You also see massively improved contaminant degradation kinetics, meaning the toxic compounds are fully mineralized, not just broken into smaller toxic pieces. This ensures absolute ironclad regulatory compliance, even as environmental agencies tighten discharge limits.
But the most compelling commercial shift seems to be the upcycling aspect. You aren't just achieving compliance, you are harvesting physical resources.
Yes, and this is where we fully realize the circular bioeconomy. We already mentioned recovering ammonia, but these advanced systems are now being integrated with microbial lipid production platform.
Wait, lipids?
Yeah. The carbon that used to be a toxic melanoidin or phenol is now being consumed by engineered microbes that naturally convert that carbon into intracellular lipids. We can harvest those lipids and sell them as feedstocks for biofuels, bioplastics, or high-value biochemicals.
That's amazing. So the overarching result is that industrial wastewater treatment is fundamentally transforming from a dreaded, capital-draining cost center into a literal resource-generating biorefinery.
It is a complete inversion of the industrial model. And the sectors most primed for this revolution are heavy emitters. Petrochemical refineries, massive distilleries, commercial food processing, pulp and paper mills, and pharmaceutical fermentation manufacturing.
The big ones.
The really big ones. This technology directly enables water reuse, which is an existential requirement in water-scarce global regions. It enables deep carbon circularity, and it perfectly aligns with ESG-driven modernization.
I have to ask about the financial friction here, though. If you look at a legacy petrochemical plant or a massive pulp mill that has fully amortized its traditional chemical treatment system over the last 40 years, the CapEx, the capital expenditure required to tear that out and retrofit the plant with electro-biological sensors, AI-driven controls, and engineered granular sludge is not trivial.
Not at all.
So is transitioning to a resource-generating biorefinery actually an immediate financial win? Or is it primarily a massive upfront modernization cost that they're simply being forced by regulators to absorb?
It's a critical question.
Yeah.
Initially, when these technologies first emerged, the CapEx was viewed as an unavoidable ESG compliance tax. But the global macroeconomic math has shifted violently in the last few years.
How exactly has it shifted?
Well, the OpEx, the day-to-day operational expenditure of legacy systems, is becoming financially ruinous. The cost of electricity required to run brute force aeration blowers is skyrocketing globally. The tipping fees at specialized landfills required to dispose of toxic chemical sludge are skyrocketing.
So the old way is just getting too expensive to maintain.
Exactly. When you model the deployment of a hybrid biosystem, you immediately slash your energy bill. You nearly eliminate secondary sludge disposal fees. And then, crucially, you begin recovering commercial-grade ammonia and biofuels.
Which you can sell.
Yes. The facility can either reuse those recovered commodities to offset its own supply chain costs or sell them on the open market. Because of that resource offset, the ROI curve accelerates dramatically. It transitions from a sunk regulatory burden into a quantifiable strategic commercial advantage.
Looking ahead, what does the next decade look like as these biological and digital systems continue to mature?
Over the next 10 years, the landscape of industrial wastewater management will become unrecognizable compared to the brute force infrastructure of the 20th century. The industry will be dominated by perfectly calibrated engineered microbial ecosystems, seamlessly integrated with advanced in situ sensors, AI-assisted predictive control, and electro-biological hardware.
It's a whole new world.
It is. The very concept of a wastewater treatment plant will be retired. It will be entirely replaced by the concept of the circular biorefinery.
Which takes us right back to our locked safe sitting at the bottom of the ocean. We have finally engineered the combination. We are no longer throwing the safe away. We are hauling it up, opening the door, and extracting the gold inside.
The ultimate takeaway for the industry leaders and scientists listening is clear. Over the next decade, your competitive commercial advantage will not come from simply treating your waste. It will come from extracting the maximum possible value from your waste streams through scalable, highly intelligent bioprocess design.
It's an incredibly powerful shift in how we view industrial chemistry and biology. Well, thank you for joining us on this deep dive into the vanguard of microbial bioremediation. We will leave you with one final lingering thought to ponder as you look at the future of industrial manufacturing. As bioprocess engineering, genetic metabolic adaptability, and AI optimization become advanced enough to flawlessly extract every single nutrient, every joule of bioenergy, and every valuable lipid from an effluent stream, will we eventually reach a tipping point where a manufacturing plant's secondary waste stream actually becomes more commercially valuable than the primary product it was originally built to manufacture? Think about the implications of that. We'll see you next time.
You've been listening to Biomanufacturing and Fermentation Technology with Prasad Urnala. Thank you for joining me. Until next time, keep engineering biology into reliable manufacturing.